Aloha. Better. By tomorrow, though, I hope that you have this perfected. So good morning. I'm very pleased to have the honor of introducing my dear friend and collaborator and our plenary speaker, Professor Andrea Goldsmith of Stanford University. I've had the pleasure of knowing Andrea for 19 years exactly. In fact, we met in 1995 at ISIT in Whistler. Andrea is the Stephen Harris Professor in the School of Engineering at Stanford. She did all of her degrees at the University of California, Berkeley. I'm going to cherry pick amongst her many amazing honors, and those include being a fellow of the IEEE and also of Stanford, the IEEE Communications Society and Information Theory Society Joint Paper Award winner, the IEEE Communications Society Best Tutorial Paper Award, and the National Academy of Engineering Gilbreth Lectureship. She's the recipient of not one but two Technical Achievement Awards from the IEEE Communications Society, one for communication theory and the other for wireless communications. She's authored an important graduate text, which I myself have used and quite enjoyed, Wireless Communications, as well as two other books with co-authors on MIMO, wireless communications, and cognitive radio. Andrea's active involvement in the information theory and communication societies is well known. She served on both boards of governors, some multiple times. She's been a distinguished lecturer for both societies, and she's been involved in numerous IEEE editorships and senior committee service. Her activism and civic-mindedness extends also to Stanford University. She's a former chair of the Faculty Senate and a current member of the Budget Group. I tried to attempt to summarize all of the areas in which Andrea has made research contributions, and you're looking at Google Scholar page after page after page, and there's quite a bit. So let me just say that she's contributed to almost every single aspect of wireless communications: adaptive modulation, beamforming, capacity results for fading channels, MIMO systems, broadcast MAC duality, relay channels, cognitive radio, sensor networks, and I decided I would stop there. Andrea has an extreme passion for education and mentorship. In fact, I consider these to be additional hallmarks of her career in addition to her research contributions. This is, of course, evidenced by her textbooks and her leadership in committees to innovate education at all levels. She's been recognized for her efforts at Stanford with their inaugural university-wide postdoctoral mentoring award. And it is not at all surprising to me that when you ask Andrea what one of her key achievements was as the president of our IEEE Information Theory Society, she points to the creation and sharing of the IT Student Committee, which continues to offer important services and activities to our students, who are, of course, all of you, the future of our society. But of course, Andrea's impact is not just through academia. She helped bring MIMO to life as a co-founder and CTO of Quantenna. However, being Andrea, one successful company is not enough, and she's now involved in the founding of Accelera, where she serves as chief scientist. And of course, Andrea being Andrea, she doesn't just win awards for research and mentorship. She's also been awarded the Silicon Valley Business Journal's Women of Influence Achievement Award. So I'd like to share a few personal notes about Andrea, and I, of course, did due diligence and intelligence gathering. And when you ask people about Andrea, there's a recurring phrase, and I must confess I've used it myself. She is a force of nature. She has superhuman energy. I can personally vouch for the fact that this woman never sleeps. It was Paris, we were on vacation, and the notes that were to become her wireless communications textbook had to be worked on at 5 a.m. Her students cautioned, though, that trying to emulate her behavior can lead to health issues. Her dedication to research is also legendary. She will not let a vacation, a collaborator's infant's napping time, going into labor, or the minor inconvenience of going through airport security get in the way of a technical discussion or making a deadline. In terms of the last one, it took the rest of us a full 30 seconds to realize that the cell phone was on the X-ray belt, and that's why she had stopped talking. You were there. Nor does dancing into the wee hours prevent her from making the plenary or the first talk of the day for one of her students or collaborators. Her students and collaborators consistently mention her generosity, her amazing ability to distill information and multitask. She engenders tremendous loyalty as she is fiercely loyal and supportive herself. So I could regale you with stories, well, more stories of Paris, Whistler, the Taj Mahal in collaboration, but I won't. I have two comments in closing. She will always tell you that her two best results are her children, Daniel and Nicole. And there's a particular quote that I think of when I think of Andrea always, and it was made infamous in the requoting by Ann Richards, the former governor of Texas. So while Andrea is coming to join us up at the podium, let me see if I can share it with you. So please help me in welcoming Andrea.
Wow, thanks for that amazing introduction, Ubli. I should probably sit down now, and then that'll be the highlight. So anyway, I am truly delighted to be here. I'm also a little bit nervous. I'm not used to being nervous to give talks, but this is a tough crowd, so please be kind. And the talk today is really going to be about wireless information theory. I'm going to start by giving you a short journey of how I fell in love with this field. And of course, love can be blind, and so there's some people that believe that wireless information theory is dead or dying. There's nothing left to do. And I hope that through this talk I will convince you that that's not the case. I'm going to talk a little bit about to infinity, how we can persevere to get results beyond 2 users. And then the beyond part is back from infinity, looking outside asymptopia. And then I'm going to talk a little bit about some dreams I have for ways that we can use wireless information theory going forward. So even though you're all supposed to think that I don't look a day over 30, I've actually been working in wireless communications for 30 years. And in fact, I think that today, in my view, it's the most exciting time ever for wireless. And the reason is that we've moved beyond the networks that we've been working on for the past 20 years, which is really about communicating with the internet or with each other, accessing information, to a lot more device-to-device communication. And I think that's really what's going to drive the future of wireless over the next decade or two. And it gives rise to all kinds of interesting problems that we're seeing research results in this conference for things like sensor networks or energy harvesting networks, body area networks where we have sensors inside the body, or even we're trying to figure out what the brain is doing or how cells communicate. And then there's the Internet of Things. So there's so many exciting wireless communication challenges out there that go beyond a lot of the traditional information theory that we've done before. So it requires new theory and new application of that theory to new problems. So I do think it's a really exciting time. So what's the caveat? Well, again, those of us that have been working in this field as long as I have, back in the early 90s when we were looking at second-generation wireless systems, we said, well, what's the killer app going to be beyond voice? There really wasn't anything. And then, boom, the iPhone hit, and the killer app became apps, anything you want to do with wireless. And we got this incredible explosion of mobile data that's growing exponentially. And in fact, this year, 2014, according to an FCC report that came out a couple years ago, we have a spectrum deficit of 300 megahertz. For all the data that we want to support today, we're 300 megahertz in deficit in terms of spectrum. And that doesn't count the Internet of Things, which is coming. It's predicted that we're going to have 50 billion devices, everything from your tennis racket to your artificial heart is going to be connected to the Internet. And so we don't have enough spectrum today for all the wireless we want to do. How are we going to support these systems of tomorrow? So this is where information theory comes in. And the real question is, are we at the Shannon limit of wireless channels? Or is there a way for us to overcome this spectrum deficit through creative innovation so that we can support all these wireless applications that we'd like to do? And, you know, often I go to conferences, communications conferences, or conferences where there's, you know, CTOs of big companies, and they always say we're at the Shannon limit. And in fact, I wanted to give you a couple of quotes from camps in the quote-unquote real world, which means kind of outside the temple of Shannon that we inhabit in the Information Theory Society. So one is that the wireless industry has reached the theoretical limit of how fast networks can go. We're 99% of the way there. Or there's another camp that says there is no limit. In fact, my good friend Steve Perlman has said that there's unlimited capacity using these small personal cells. So I kind of put these quotes in two categories. The first one is that we're at the Shannon limit, and the second one is that Shannon was wrong. In fact, there is no limit at all. Okay, so was Shannon wrong, or is he now irrelevant because we're at the Shannon limit? In other words, do we need to go find another hero because, you know, there's nothing more to do with Shannon? You're all supposed to gasp when I put a red X through Shannon's face. So, of course not. It's not the case that Shannon was wrong or irrelevant. So what's the flaw in the logic of these people that are giving these quotes? They're not stupid, and they're certainly working in this field. So there's a couple of flaws. Often they're using the single user capacity formula for comparison. Or they let power go to infinity, which we know we can't do, or they let bandwidth go to infinity. They use small cells in terms of aggressive frequency reuse. We don't know the Shannon capacity of cellular systems in general, so we can't really say how good we can do with small cells. Or there's the final frontier of massive MIMO. So that's how, when they say that, we're at the Shannon limit, they either don't take these things into account, or there is no limit. It's because we can let all these different dimensions go to infinity. Okay, so I believe very strongly that Shannon theory is more relevant today than ever before. In fact, we don't know the Shannon capacity of most wireless channels, and I'm going to talk about some of those open problems in my talk today. So we can't say we're at the Shannon limit because we don't know what the capacity of wireless channels are. In particular, when we have feedback, especially with time-varying channels or channels with memory, when we have channels outside the asymptopia of having delay constraints, energy constraints, or hardware complexity constraints. Interference and relay channels have been open problems for 30 years. Cellular systems, we really only have the results of Weiner and the extensions of that. We don't understand how to incorporate frequency reuse into the study of cellular systems in a fundamental way. And ad hoc and peer-to-peer networks have been open problems for a long time as well. Finally, and an area that I think we need to do more in this community is looking at things like multicast and common information, because that's an area that's going to grow. A lot of people want to see the same information, and yet we often only look at private information in the problems that we're studying. So all of these are open problems. We don't know the capacity of any of these channels. And again, taking from a lot of my startup experience, it's not just that we want to solve information theory problems because they're beautiful to work on, which they are, but they also really give you crucial insights to designing good systems. And the other sub-theme I want you to walk away from this talk is that theory matters. That what we do in this conference and in our work has a huge impact on wireless system design, and we need that impact going forward if we're going to solve all the challenges that I mentioned in terms of future systems. But of course, wireless information theory is also a lot of fun, so that's another reason to work on these problems. Okay, so now I'm going to take you back on a little bit of a journey in time as to how I first got started working in wireless information theory, and the sub-theme of this is that the key to good theory is really asking the right questions. So I went back to grad school in 1989. So this is me in grad school, young, unmarried, no kids, happy-go-lucky. And I went to Berkeley, as Ubli said, I did all my degrees there. So I did my undergraduate work for a few years and went back. And I had the pleasure and honor of working with Praveen Varai as my advisor. And so it was 1989, I wanted to work on wireless because it was a hot field, and there was a huge debate going on as to what should the next generation of cellular standards be. Should it be TDMA, FDMA? Should it be GSM? Or should it be CDMA? So Qualcomm was making a big push for CDMA. And so I asked Praveen, how do you know? How do you figure out what the best technique for cellular system design should be? And he said, well, what does Shannon say? Now, Berkeley in 1989 had no information theorists. It had no course in information theory. There was nobody working in information theory. So who's Shannon, I said. So anyway, I went to the library. Back then we had libraries, and you went to libraries, and you got books out of the library. And I started on my journey, one of the most enjoyable journeys of my career, which was to read Gallagher's book. And in Gallagher's book, he talked about, in chapter 7, I believe, the capacity of a frequency-selective fading channel. Static, not time-varying, but frequency-selective. And basically, what he does is he breaks that channel down using a Karhunen-Loev decomposition into a set of parallel channels. Then he solves for the capacity of the parallel channels, takes the limit, and you end up getting this beautiful capacity result, which says that the way that you achieve capacity on this frequency-selective fading channel is you put more rate and more power into the channel when the channel's good. You use this water filling in power and adapt the rate over frequency according to the characteristics of the channel. When the channel's good, you put more rate in. When it's bad, you put in less rate. So the problem for me at that time is that this was a beautiful result, but it was for static channels. And the real argument that Qualcomm was making was that CDMA is better because it has time-varying power control. It adapts to the interference and to the channel. So I said, well, okay, how do I find the capacity of a time-varying channel? So I looked for time-varying channel capacity. And the idea was a flat fading channel where you know the channel at the transmitter and receiver. And again, going to the library, I pulled out this book, the second edition by Wolfowitz of Coding Theorems of Information Theory. And he has that the capacity of a channel is basically if you have a channel that has different channel states with different probabilities, the capacity is just the average of the channel capacity in a given state times the probability of the state. And, you know, I think information theorists back in 1964 were more macho than they are today, because today, if there was a simple proof, the author of a book would say, you know, put it as an exercise in the homework. But Wolfowitz just said, the proof of this theorem is so simple that I'm not going to admit it. It's so obvious that you shouldn't even have to think about how to solve it. So anyway, there was another set of work at the time on time-varying channels. This is what I call a pessimist view, which said if you have a channel capacity for a given rate and channel, and the channel is varying arbitrarily, you assume the channel's kind of out to get you, and you optimize the input for the worst-case channel. So the idea that I had was, why don't we combine the notion of Gallagher, which is that you adapt to the channel state, with this notion of the arbitrarily varying channel, so you just adapt to the channel, not to the worst-case channel. And that's basically how I got the result for the capacity of a fading channel. So this was my first result. And it's basically water filling in time. Rather than water filling over the frequency domain, you do water filling in time. When the channel's good, you put more power and rate into the channel. Okay, so I got this result, and then I went off to Bell Labs in 1991 to do an internship in Crawford Hill. And in fact, the very first time I presented the time-varying capacity result was in Murray Hill to Aaron Weiner's group, and everyone from the Technion goes to that group in the summer, so there was Lempel and Ziv and Shlomo who asked all the questions, but fortunately I didn't get any wrong, and that started a number of collaborations after that. So anyway, 1991, I was working with Jerry Fischini, and I told him about this time-varying capacity result, and I said, is there a way to make it more practical? How do we implement it in practice? So I went off and read a paper that he and Jack Saltz had written about deriving the probability of error. And basically, inverting that expression, I got an expression for the constellation size according to a particular signal-to-noise ratio for a fixed bit error rate. And it turns out that you can adapt the rate according to that time-varying SNR to get this formula. And then if you want to do the maximum rate, you just maximize over your power constraint. So the math here isn't important. What's important is that this is exactly the same as the capacity formula on the previous slide. So it's a bridge between theory and practice. Same formula. The only difference is a coding gain, which depends on the bit error rate. So here's an expression of the capacity for different bit error rates, the adaptive modulation rate according to those different bit error rates, and you can close the gap with a trellis code. Okay, so this was published in 93, and then the Superimpose code in 94. This was the first time for wireless information theory that Shannon bridged the gap between theory and practice, because this was the first result that said adaptive modulation, as predicted by Shannon, is optimal. And this was the first adaptive modulation proposed for fading channels. At that time, I had never done a startup. I didn't think to patent it. Ericsson patented it 2 years later. And around the same time, the work of Gallagher's book saying you should adapt in frequency adaptive modulation was patented by Chiaffi and Chow for DSL. So this was really the first time in the early 90s that Shannon theory predicted what was optimal in practice. We implemented it in practice, and it turned out to have the best performance of any system. Okay, so that's my early days. It's been a very fun ride. So Ubli mentioned some of the things I've worked on, and this is a fairly exhausted list, and it's not just me, and I can't put up the names of all my collaborators or everybody else that has worked on these fields, you know, fading channels, multi-user fading channels, and time-varying channels, and so forth. So the question is, okay, we've been working on this for 20 years. Is there anything left to do? In addition to working on this, we've had a lot of impact. So if you look in particular at the Wi-Fi standards and the cellular standards, everything we've done is based on a lot of the work that's come out of the information theory community. So we've had a lot of impact. We've done a lot of work. Is there anything left to do? Why are we still working in wireless information theory? And that's going to be the remainder of my talk. What is the next frontier? So I'm going to talk about towards infinity, looking at larger networks than 2 users. I'm going to talk about coming back from infinity, moving outside asymptopia. And then dreams. What else can we do with the tools and methodologies that we have? Okay, so.
To infinity and beyond!
This is the first time I've used sound in my presentation. Okay, we'd like to get at least more than 2 users, all right? We don't even, not even close to getting close to infinity. How about more than 2 users? Can we do that in terms of ad hoc network capacity? So what is an ad hoc network? It's a fully connected network. Every node can talk to every other node. When you see these routing lines in ad hoc networks, they're artificial. There's no such thing as a multi-hop route fundamental to a network, because if you transmit at any one node, you can hear it at every other node, just with a varying signal to interference and noise ratio. So to characterize the capacity region of an ad hoc network, it's an n times n minus 1 dimensional region. Now, the topology, of course, combines broadcasting. So from this node, I'm broadcasting out to multiple nodes. It combines the relay channel, because I can go from one node to other nodes, interference channels, multiple access channels. So all of the canonical channels that we've been looking at for the last 30 years are kind of subsumed in the topology of this ad hoc network. And the lower bounds that we have for these networks tend to use the coding strategies of these canonical systems, and I'll talk about those in a moment. In general, good upper bounds have been hard to find, and actually that's one of the things I'll talk about a little bit later is there's many open problems in terms of coming up with good upper bounds. Okay, so the encoding and decoding techniques that have arisen in the study of these canonical small networks are things like superposition coding, Gelfand Pinsker binning, or precoding against interference, rate splitting, interference decoding and cancellation, coded time sharing, and then all the relay techniques, in particular the noisy network coding that's come about in the last couple of years. So these are kind of the canonical techniques that we've been applying to the classical models for 2-user networks, like the broadcast channel MAC and so forth. Okay, so why is it hard to come up with the capacity of these ad hoc networks? Well, the challenge is really the complexity of the encoding and the decoding schemes. So if I wanted to find a coding scheme for an ad hoc network, what I have to do is for each node in the network, I have to decide which technique am I going to use at the encoder and the decoders that it impacts. So I'm going to do superposition, rate splitting, binning. Do I do interference decoding or partial interference decoding? If I rate split, do I time share and so forth? And the challenge is that the encoding I do at one particular node affects the encoding and decoding at the neighbor. So for example, if this is a broadcast channel and I do superposition coding here, then I'm going to, if this is the worst user, then I'm going to do controlled interference to the worst user, and the better user is able to cancel out the interference. But if I have another user over here who I'm not considering in my code, then I just get uncontrolled interference there. That's if I do superposition coding at that one node. What if I do rate splitting? Well, with rate splitting, I can partially decode if I rate split according to the interference here, but again, I have uncontrolled interference to all the other nodes that I'm not doing the rate splitting with respect to. And if I do binning, then I don't need to do anything at the receiver that I'm binning the known interference to, but again, I'm causing interference to other nodes. So that's for a single node in the network, and then I have to look at all the nodes in the network in terms of figuring out the encoding and decoding ideas. So how do I combine these different techniques in a network, especially when the encoding and decoding possibilities grow exponentially with the number of nodes? So as the network gets bigger and bigger, I get, more and more decisions about how am I going to combine the different techniques. And that's really why we've been stymied to a large extent in solving for capacity of ad hoc networks with more than 2 users. Okay, so I'm going to focus on a one-hop network without any relay. So I'm taking relaying out, and this subsumes the broadcast channel MAC, interference and cognitive radio channels. And I want to in particular focus on having common information to subsets of users, because that's also an area that we haven't really looked at very much. So I can have any set of transmitting nodes and any set of receiving nodes, and I can have common or private information for different subsets. Okay, so the typical capacity approach in solving in these networks is I define an encoding and decoding scheme for all nodes, some combination of known techniques typically. Then the rate inequalities associated with that encoding and decoding tell me how many code words I can reliably decode and the number of code words to pre-code against interference. So basically I define these encoding and decoding schemes and the rate inequalities fall out so that through the packing and covering lemmas I can get reliable decoding. And then sometimes I can get tight upper bound. So just to illustrate this for a fairly simple channel, and this is based on joint work with Ivana, Gerhard, and Shlomo from a few years ago, it's a cognitive radio channel. So I have a cognitive radio receiver which gets the message of the non-cognitive radio, and I'm going to use a combination of rate splitting and binning at the cognitive encoder. So the cognitive encoder is going to rate split so that it can help the non-cognitive receiver in terms of receiving. So that rate split is basically to take the information that the cognitive encoder knows and use it to help the decoder at the non-cognitive receiver, and the non-cognitive encoder doesn't do anything. It doesn't know anything about the fact that there's some other radio in its band. Okay, so the cognitive radio, which is the only thing that's in action here, splits its message. It uses two code books pre-coded against the known interference, and it cooperates in sending that message to the non-cognitive receiver. Okay, so out of that you get these rate regions. Out of this, so I've defined a scheme, and now I get a set of rate regions, which rate inequalities, which are needed to define or these rate inequalities say, below this rate, I can get reliable decoding, and where they come from has to do with the construction of the code. So I get the contribution of the common information to the rate at the cognitive radio receiver, but then I also pay a penalty in the binning. So whenever you bin against interference, you subtract that from the rate. So the second term there is the rate penalty for binning, and then I get this common information which I'm sending to the non-cognitive receiver to help him decode. Okay, so the details of this are not important. What's really important is kind of the high-level notion that once I define my encoding and decoding scheme, I get these rate inequalities. Okay, and it gets complicated really fast. So if I go to a more complicated scheme than the very simple one I just showed, and I put this up because I wanted to show a picture with like a whole page of rate inequalities, but I didn't want to embarrass anyone, so I did it with joint work between me and my former postdoc, Stefano Rini. So this is actually in one of our papers. All right, you look at this, how do you get any insight from this page of equations, right? It's very hard to see what's going on. And again, it's the same idea. All the rate inequalities come out of the specific scheme we're using, which has superposition, coding, binning, broadcasting, rate splitting, et cetera. And this is for only 2 users and 1 distribution. So think about what if we have a cognitive radio with 3 users or 10 users? It's not going to work, okay? So the question is there a better way? And this is a paper that's hot off the presses, literally submitted yesterday, although Stefano has presented these results before at ISIT, is a unified way to do this without resorting to the technique that I just described. So the approach works for any single hop memoryless wireless network with any combination of private and common information. So common information can go to any subset of users. It basically determines the largest achievable rate region for all combinations of random, so it only works for random coding, not for structured codes, any combination of random encoding and decoding techniques. And there's 4 steps, which I'm going to talk about in more detail. First, you do rate splitting, and through that you get user virtualization. You make the problem harder by creating more users that are virtual, but by making the problem harder, it actually makes it easier. The next step is you use a graph to define all possible superposition and binning, encoding and decoding strategies. The graph is used, basically it's a representation that constructs a graphical Markov model that represents all the statistical relationships of the code word. So that's the thing that gets hard as the network gets big, is how do you keep track of the statistical relationships? If you're superposition encoding at one node, how does that affect the next node, and so forth? So the graph captures all that, and then you basically get the error analysis for free out of the rate relationships that come from this graph. So let me illustrate what's going on in more detail. So again, here's the system model. I have some set of users. I may use multiple transmitters to send the same message to a given receiver. I may have common information that's going to multiple receivers. So this is a very general setup for any number of users and any combination of common and private information. And the messages can be sent over one or more transmitters and received by one or more receivers. Okay, so the user virtualization, what I do is I take each of my actual users and I use rate splitting to define virtual users. Okay, so the idea is that, say, this user 1, I'm now going to rate split his message into 3 pieces. Now, he still needs to get all 3 of those pieces because I'm preserving the rates of that user. Then why do I want to rate split? Well, by rate splitting, it may be possible for receiver 2 to decode part of the message and subtract it out. So the rate splitting is actually helping this other receiver get rid of interference. And same with the receiver M. So that's what I do to user 1. I can also make user 2 add a virtual user to user 2. And then, of course, I need to get that information at user 2. But again, maybe I do the rate splitting so that I can subtract interference. And maybe I don't do anything to the common information user. So first I do this rate splitting to create these virtual users. The virtual users have the benefit of making it very easy to embed common information and also to allow for the rate splitting where I see how I decode interference out. Okay, now the next thing, and this is really kind of the most important aspect of this approach, is a graphical representation of the coding. So basically, the code words, so I'm going to use a graph to represent how I'm doing this coding over this very large network. And so the nodes of the graph represent the code words. These are the random code words, the random variables. And the premise here is to use a graphical Markov model, which was introduced by Perl, and it's used widely in other areas, not so much in information theory, to capture the conditional dependency of random variables when you have very complex relationships between random variables. And we're going to do that here for the ad hoc network coding. So here I'm using the graph to capture the dependencies of the code words, which are random variables, due to the coding operations, where I'm either doing superposition coding or binning. So if I do superposition coding, there's a couple of constraints that must be put into the graph. So in particular, so suppose I'm doing superposition coding on the standard broadcast channel. So this is the common information of the broadcast channel. This is the worst user, and this is the better user. So then so the common information is the bottom code word, and then I embed the code word to the worst user, and then on top of that I put the code word to the better user. So you have that if a node is superimposed over another one, it is also superimposed over the parents. That's one of the constraints in the graph for that relationship of superposition coding. And then binning, binning is how I'm picking code words to pre-code against interference. So basically, the constraint in the graph for binning is that I can't form directed cycles because that would mean basically I was creating a random variable that was conditionally dependent on myself. So that's one of the constraints of the binning. And the other is that I can't do both superposition coding and binning simultaneously because that would mean I would be both pre-coding against interference and subtracting the interference out, which doesn't make sense. Okay? So this is how I create the graph, and I can do this again for any number of nodes, any number of code words, in any particular scheme where I do a combination of superposition and binning. Okay? So then the encoding and decoding procedure is that first, if I'm going to do coded time sharing, I pick the random sequence for coded time sharing. I generate the codebooks via superposition. Then I encode the messages via binning. So I pick the code words in the codebook according to the interference that's generated. Then I transmit the messages, and I do decoding via typicality, so standard decoding techniques here. Okay? Now, how do I get my rate region? And where does the reliable decoding come from? There's many ways to make an encoding or decoding error. So I could decode an error, a top code word that was superimposed on a lower one. I could decode the lower one in error, which means for sure I would decode the top one in error, so forth. And I can make errors at any one of the receivers or any combinations of receivers. So there's many ways to make encoding and decoding errors. So if I pick any particular error event, in order to get vanishing error probability of that particular event, I basically need two things. I need the packing lemma, which tells me how many code words I can decode reliably, how many code words I can pack into this signal space. And then the covering lemma is my penalty for binning against interference. So if I have a particular code word, I have to pick, code book, I have to pick a particular code word that I'm binning against, and that's a penalty in my rates. Okay? So between the packing and covering lemmas, this defines a set of rate regions, and then I can ignore some error events because they're dominated by others. So if the ones that are dominating have vanishing error probability, then the ones that are dominated by that one I don't need to worry about because they will also have vanishing error probability. Okay, so for every error event, the packing and covering lemma give me these rate constraints. So I get a different rate constraint associated with every error event. And when I look at all the error events, I eventually trace out the achievable rate region. And it turns out that that rate region is, or these different lines in the rate region are very easy to draw based on the graphical Markov model. So I can just write down all these rate inequalities. That long string of equalities, I just write them down. I don't even need to think about them. They fall out of the graphical Markov model, except that there's a couple of very minor binning restrictions I need to put onto the binning in order for that to happen. Okay? So just to summarize this approach, I've taken the original channel, which is any single hop channel, any combination of messages, common information, private information, and so forth. I enhance it doing the user virtualization. I then create this graphical Markov model to capture the coding operations. And out of that, I can just write down the rate expressions which define my achievable rate region. And that determines the largest achievable rate region of any single hop wireless network for all combinations of random coding techniques and with any combination of private and common information. And it subsumes all known results for these types of networks. Okay, now extensions. Achievability, we haven't looked at structured codes. I think it'd be very interesting to combine this technique with relaying. We're not sure that we can do it, but if there's a way to use this graphical Markov model, that would be great. Parallel channels are always an interesting channel to look at. That's where all the MIMO work came out of, even like the capacity of a frequency selective fading channel is really a parallel channel capacity result. So I think it'd be interesting to look at that, and also the use of feedback. Now, upper bounds, it's not clear that this technique can be combined with any of the upper bounding techniques, but maybe through this rate splitting and giving some of the rate split information, you might get something like the more capable channels that allowed us to solve for the MIMO channel capacity and so forth. So I think the moral of this is that there's a lot to be done, a lot of interesting work in going towards infinity. There's no limit on the number of users in this technique. And finding ways to unify what we know to look at larger networks, I think is a very promising and important area for research, especially because when you look at things like the Internet of Things and sensor networks and so forth, we really need to solve for capacity of networks with more than 2 users, because these are going to be networks with lots of users. Okay, so now let me go to the second part of the talk, which is coming back from infinity. Getting fundamental limits outside asymptopia. So why should we back off? Why don't we live in asymptopia? It's a beautiful world to inhabit. But the reason is that if we want to better inform practice, we need to look at the constraints that happen in the real world. And I like to quote my dear colleague, who we miss a lot, Tom Cover, that theory is the first order term in the Taylor series expansion of practice. So if we understand some of the fundamentals imposed by the practical constraints of systems that we build, then maybe we can design better systems, and maybe we can bring that back to our theory. And that's, in fact, the next part of my story, which is why
I want to be a billionaire so freaking bad.
Okay, that's not why I did a startup, actually, even though most people think it is. It really wasn't to make money, but it was to build something again. So this is me in Silicon Valley in 1986. This is actually the middle of Santa Clara. There's a huge Broadcom building sitting there now. This is my first job at Maxim, building an antenna array. Okay? So I built the antenna array, then I went back to Berkeley in '89 and spent 20 years doing a lot of theory. Okay? And a lot of that theory was motivated by the work I did in 1986 on wireless systems. So 20 years later, I wanted to build something again. And that's why I started Quantenna, was to say, okay, I've been doing theory for 20 years. I've been working on MIMO systems and adaptive modulation and fading channels. Does that theory matter in a real system? So if I'm going to build a state-of-the-art product, you know, in startups, they don't care how many papers you've written or what your H-index is, okay? They just care about the dollars, okay? If you're going to build a successful product, does theory matter? Does it really help you build a better product? And in fact, Quantenna just announced 10 gigabit per second wireless Wi-Fi, okay? We did build a better product using the theory that we knew. We put everything into that chip. Everything that we've written about is in that chip, okay? And it is the best performance on the market. So theory matters. And also, I wanted to bring some of the knowledge of building something, again, back to my research. So what would I learn from building something that I could then take back and come up with new research problems? Okay, so bridging theory and practice is, I started in practice in 1986. I went and did a lot of theory. I went back to practice, and then I was going to go back to theory. Okay? So what did I learn from all this? Academics have great jobs, okay? If you ever want to appreciate your job, do a startup, okay? It's a really, it puts hair on your chest, even the women. It's a really tough job, okay? Information and communication theory heavily influence wireless system design, heavily influence it. Okay, you meet people in standards meeting, they've read all your papers. That was a shock to me. We think we just read each other's papers, but actually people out there that build systems read our papers. They know us and they implement our ideas. Kind of one of the demoralizing things is that after 30 years of information and communication theory, what we built costs about the same as a cup of coffee. Okay, so it's very hard to monetize a lot of the information theory that we do, even though it has a lot of impact. In wireless, analog matters, and this is one of the big lessons I brought back to my research. Okay, we that inhabit the green transactions, everything stops after the A to D. Okay, we don't think about D to A's or A to D's or anything that's going on in the analog circuitry, but you go build a system, that stuff matters a lot. Okay, and understanding what goes on in the blue part of that picture will really have a lot of impact if we as a community can do that, okay? And then complexity drives the cost, size, and energy. Why is that chip $5? Well, it's small. It has fairly low processing power because if I put more processing power into it, I need a bigger chip, I need more energy, and I can't sell it, okay? So all the work that we're doing on low complexity and energy constraints and so forth has a huge impact on the industry. Okay, so when we look at some of the assumptions that we make in theory, and what's true in practice in state-of-the-art wireless today, there's a huge gap. And so if we can look at some of this stuff, maybe we can actually impact theory even more. So there's been a lot of work, especially recently, but even going back over several decades on ways to back off from infinity in terms of looking at finite block length codes, which help with energy, delay, et cetera, looking at finite energy systems. I did this with one of my early PhD students. And there's also a lot of other work going on as well in finite energy systems, all this energy harvesting and so forth. Pulkit Grover has done some beautiful work on looking at finite processing power in chip design, coding and encoding and decoding techniques. There's been some great work on finite precision A to D converters when you don't have full precision. And I'm going to talk about two areas that I've been working in, finite rate sampling and a little bit about feedback. So the A to D converters really are not that fast in real systems. They're expensive and they consume a lot of power. So when we go to these wideband channels, we can't necessarily sample at the Nyquist-rate. So how do we study capacity of those channels? And how do we learn how to communicate over channels that are sampled below the Nyquist-rate? In other words, how do we bring together sampling theory from Nyquist and Shannon capacity theory? So what we looked at, and this was joint work with my student Yuxin, Shannon, Rini, and Eldar, was if we don't sample at the Nyquist-rate, what's the optimal input signal? What's the trade-off between capacity and sampling rate? And what's the best way to sample? And is it one of the techniques we know, or maybe we need to discover a new sampling mechanism to get capacity achieving sub-Nyquist sampling? Okay, so this work was done several years ago, so some of you or many of you may have seen it before. To get the capacity of the sub-Nyquist sample channel, if you just have a single branch, a filter, and a sampler, you end up getting a capacity formula that looks a lot like the Gallagher formula that I showed at the very beginning, except that now you have an alias channel. So basically, you sample the channel, you alias it, you can control the alias channel through the filtering, and then you get the capacity of that alias channel. And basically, the way you optimize your input is you do water filling, but over the alias channel. So basically, you only put power into the part of the spectrum where the alias channel is best. Okay? So the problem with that is that, surprisingly, it's not monotonic in sampling rate. So even if you sample faster, you may end up with the lower channel capacity. And the reason is that for a sparse channel like the one I've shown here, at certain sampling rates, the islands collapse on each other and you lose degrees of freedom. Then when you increase the sampling rate, you get those islands back and you get more degrees of freedom. So that's why it's not monotonic. So if you look at this, you would say, well, you know, there's got to be a better way to sample because it doesn't make sense intuitively that this would be non-monotonic in sampling rate. And indeed, there is a better way to sample. The state-of-the-art in sampling is filter bank sampling. And it turns out that if you have enough branches in your filter bank sampling, so that each branch consists of a filter and a uniform sampler, and I'm keeping the sampling rate the same, so the more branches I have, the sampling rate in each branch goes down linearly, then if you have enough branches, you get monotonic increase in the capacity with respect to the sampling rate. So this is showing that it's monotonic in the sampling rate. But this formula is interesting because it looks like a MIMO channel capacity formula. Okay, it has a log det. So where is that MIMO stuff coming from? Well, the idea is that in this filter bank sampling, for each frequency, you can think about your frequency as like a different input to a MIMO channel, except that the frequencies at integer multiples of the sampling frequency get combined. But now that I have the filter banks, I have different branches, so different ways of combining them depending on how I design my filters. So basically, I get pre-whitening of the noise, because it's going to get sampled. The MIMO decoupling is from the fact that I have these different branches, so I'm combining the alias signal that I'm getting in the different branches, and then I do water filling over the singular values of the alias channel. And that's where this MIMO formula comes from. Okay? Now, it turns out, and this is, again, interesting from a practical perspective, that I don't need a filter bank and uniform samplers. I can just have a single modulator, and that's equivalent to the filter bank, and it gives me the exact same channel capacity. And that turns out to be optimal among all time-preserving non-uniform sampling techniques. So I don't get anything in terms of capacity by sampling in a non-uniform way. And this generalizes, so if I don't know the channel and I want to look at universal sampling, okay, so what I said before is that you design the sampler based on a known channel. What if you don't know the channel? Well, in that case, we use a metric called the Minimax universal sampling, where for any channel state, you pick the sampler that minimizes the capacity loss by using that sampler versus the optimal one. And that's better than the compound channel capacity, which is kind of more of a worst case. And if you look at a multiband channel, where you have a sparse channel, some of the bands are occupied and some are not. So this could be an OFDM channel where you're only given a few tones, or it could be a cognitive radio channel where a few of the subbands are available. It turns out that the optimal way to build this Minimax sampler is based on random sampling. So that was kind of surprising to us. So the result here is that you can determine the Minimax capacity loss at high SNR. When you're sampling at the Landau rate, which is the minimum bandwidth occupancy, that loss only depends on the sparsity. So beta is how many subbands are occupied. And you can achieve that with random sampling, with actually any mixture of distributions. So the random sampling says that the coefficients of the Fourier transform of the sampler is random. And this is, as far as I know, the only result demonstrating the optimality of random sampling. Okay. Now, I want to talk, I'll spend a few minutes talking about another thing we've done on Sub-Nyquist, which is Sub-Nyquist source encoding. And this is joint work with Alon Kipnis, Saki, and Yanina as well. So if we have a network, whether it's Sub-Nyquist sampled or not, if we can Sub-Nyquist sample the source, then we have fewer bits to transmit. So we've really reduced the rate that we need. And so when you look at rate distortion theory with sampling, it's kind of unifying, just like the channel capacity results did, it's unifying sampling and source coding. As the sampling rate goes to the Nyquist rate, you just get a classical source coding problem. And as the rate of your compression goes to infinity, it's just a sampling problem. So how do we bring these together? So the problem statement is basically we want to find the distortion now as a function of the compression rate between the source encoder and decoder and the sampling rate of our original source. And the metric that we're going to use is mean squared error, which is the traditional metric in source distortion. Okay, so, whoops. Yeah, okay, all right, so I have 5 minutes. So let me just go to the main result. In fact, so the main result is that you can derive this distortion rate function. It's a function of minimum mean squared error, and the distortion that's introduced through the compression. And the best way to show this is a picture, especially since I only have 5 minutes. So basically, the properties of the solution is that the sampling distortion is this red part of the curve. That's the distortion that's introduced through the sampling. And then the compression introduces the distortion below this water filling line. So the water filling line is based on my rate. It gives me a water level. I have distortion from those components, and then the red part is the distortion associated with the sampling. And this actually relates back to a lot of beautiful older work by Zbakov and Ziv and Wolf on rate distortion. Let me skip that. I just want to say a few things about feedback. I think this is one of the most beautiful open areas. So basically, Shannon said if you have no feedback, you get error exponents that fall off linearly. If you have perfect feedback, you get this very sharp fall off of the error exponent, and that has a lot of interesting implications when you have delay and finite rate or finite block length. Younghan has a beautiful result, won the best paper award on feedback with additive white Gaussian noise, which says if you have noisy feedback, you're out of luck. You go back to the very slow error exponent. And we did some recent work which showed that basically if your feedback rate is much bigger than your feed-forward rate, again, you get this very fast fall off of the error exponent. But more broadly, I think that there's a lot of interesting open questions with feedback. Feedback increases capacity. It actually works as a form of cooperation in multi-user channels because if you have a broadcast channel, for example, and you feedback the signal from one of the receivers, you're actually getting information about the code that was sent to the other one. So there's a lot of interesting aspects of looking at capacity with feedback, and I think the most important reason to study this problem is if you look in practice, how do we use feedback in real systems? We use 1-bit ARQ, or maybe we use hybrid ARQ in a really sophisticated system. We use feedback very minimally in real systems, and I think that's because we don't understand fundamentally how to use it. It's really an open problem, and if we could figure out how to use it, we could build much better wireless systems. They only use basically channel state information feedback in ARQ. That's all we're doing in practice. There's a lot more you can do with feedback. Okay, so let me wrap up and take a couple minutes talking about dreams and challenges. So the next frontier, I've talked about, some areas of wireless network capacity that's open. Some of the areas that I think are really interesting, in fact, my postdoc Jinwan is giving a talk on Friday about parallel heterogeneous networks. So parallel channels has been a workhorse of solving capacity. It's how I got the capacity of the time-varying channel. It's how Gallagher got the capacity of frequency-selective fading channel and MIMO channel. But what if the channels aren't homogeneous? What if they're different? So in that work, we have a broadcast channel and a multicast channel. But I think that networks of the future are going to be heterogeneous. You're going to be getting data over your cell phone and over your Wi-Fi and over your Bluetooth. What's the fundamental capacity of a system like that? Coming back from infinity and expanding our horizons. And these are my last few slides. So how do we apply our analysis tools and methodologies to new disciplines? In a fundamental way. Not just take mutual information and apply it, but really try to understand in a fundamental way different systems. And I have the Center for Science of Information, led by fearless leader Wojtek, to thank for me thinking about these problems in biology. So when we were writing the proposal, I thought, well, what do I know that weighs in on biology? So I said, well, the brain kind of looks like a network. So maybe we can think about applying information theory to understand how neurons encode or decode. It turns out actually one of the most powerful ways to use what we know is not mutual information or encoding and decoding, but you can inject a signal into the brain in a particular area and reduce the effects of Parkinson's. They don't know why. They know the shape of the signal. They know it works. They don't know why. Can we help understand that? That would be interesting. Or an epileptic fit, which happens because a signal moves, an oscillating signal moves through different parts of the brain. They don't understand how it moves or why it moves. Can we stop that through some kind of filtering or other thing that we know how to do? Maybe. So there's a lot of exciting things to do in the brain as information theorists. And the other area that I've been working in is microarrays as multi-user communication. So I'll just take 1 minute to talk about each of these, and then I'll wrap up. This is work by Nima Sultani, who he presented this last year at ISIT. If you want to figure out how neurons are laid out, you can use directed mutual information because that has, it's a metric of causality. So if you have a brain spike here, that'll cause this guy to spike, and eventually the spike will make its way over to the last neuron in the connected network. But the problem is, because these are connected causally, how do you know if you see a spike here that it was caused by this node instead of this node? Because they're all causally connected. So you can use actually propagation delay to see how the propagation of that spike train is delayed in each hop of the network to get a much better inference about the connectivity. Now, this is based on actually measuring spikes coming out of the neurons, and that's not easy to do. But if we could do that or find ways to do it, then there's a couple interesting things we could study. We could study learning. So if you see how the brain is connected at different stages of a person, you see how they learn, because that's all about connecting neurons. Or if you look at degenerative diseases, you can see how those are progressing, or you might even be able to diagnose them. This is still just using mutual information as a tool. It's nothing fundamental here. It's just using it as a tool to observe the connectivity in the brain. And there's a similar way to use a tool that we know for microarrays, which Waterman mentioned in his talk, where basically the idea here is you take a tumor tissue, you extract RNA from it, you put it on this microarray, where you basically got all these genes that are superimposed on top of each other. And if you can figure out what the gene composition is in that tumor tissue, you can get much better prognosis, because if you have certain concentration of genes, your prognosis is not good, and if you don't have those genes, your prognosis is good. But they're all muddled on top of each other. And so my postdoc working on this started talking to my postdoc started talking to a postdoc in the med school working on this. And he said, you know, this looks a lot like CDMA. You've got all these unique signature sequences that are superimposed on top of each other. Why can't we use, like, known techniques for deconvolving signals to figure out the gene sequence? And that's actually what we did. We took this microarray data. We could figure out blindly what the different genes are and what their concentrations are. And we just published this in a computational bio journal last year. So again, what we're doing here, we're not doing anything fundamental, which is disappointing for information theorists. We're really just using the tools that we have and applying them in new ways to interdisciplinary problems. What we really seek is fundamental questions that we can answer with information theory, and that's still out there. Okay, my time's up. 50 minutes. All right, so let me just wrap up. I think there's many new frontiers to explore in wireless information theory. Asking the right questions is more important than getting the right answers. That's especially important for students to know. Theory informs practice and vice versa, and I have to say the most fulfilling moments of my career is when I actually saw that the theory that I'd been working on for a long time made a big difference in practice, and then took what I learned from building real systems and brought them back to my research. So I recommend people, if you have the opportunity to do either one of those, crossing the bridge. It's very rewarding. And finally, it remains to be seen, I think, whether information theory informs biology in a fundamental way. But even if it doesn't, if our tools can help us understand how the body works, how the brain works, how disease evolves, we will have had a huge impact. And with that, I'll wrap up. Thank you.
So we have time for a couple of questions. And we have volunteers with microphones. Can you? Right here. Yeah.
Thank you, Andrea. Very thought-provoking talk. I wanted to ask you about the filter bank issue you brought up. So if I understood it, the filter bank basically has very similar characteristics to a MIMO system. Mm-hmm. So does that mean that there's diversity in the filter bank? I mean, are the filter banks creating diversity somehow in the signal?
Yes, exactly. So basically, if you only had one, so the filter bank is introducing this set of combined terms. So basically, or one filter. So if I only had one branch, I would have one node here that was combining basically the aliased input going through the input going through the alias channel, okay? And I get to pick the input, so I can put power only at the input places where I'm going to get the most bang for my buck coming out of the alias channel. So it's a combination of diversity and MIMO in the sense that all of these different branches combine in one output for one of the branches, and then I have all the branches together. So you get this combination of diversity combining in one branch, and then all of the different branches that you get to use for your capacity expression. So it's a combination of diversity combining and MIMO, and a MIMO channel, which is unusual. I mean, that's what makes the formula a little bit different than the traditional MIMO formula, and the capacity formula would just be combining the inputs, right? It wouldn't be anything different than that.
Okay, thanks.
Thank you, Andrea, for excellent presentation. So, yes, so I have a question about the delay part. So
Sure.
We start with the waveform channel, and we know that by Nyquist sampling, we can essentially discretize it in time. But then when it comes to the looking into delay, its impact, always we limit ourselves into, at least to my knowledge, to the same discrete level that Nyquist sampling has given us. So do you see a point of going back and revisiting the waveform channel and see how delay, do you know of any work who has not?
So which delay? The delay after the A to
No,
D converter?
let's say you have the sampling, and then we want to see how the delay in a network improves performance or degrades performance. Always the unit of delay is either one symbol of like one Nyquist interval or a coded block, which doesn't need to be that.
Yeah, so I think that the real challenge in terms of the problem with delay is, are you talking about when you have feedback or no feedback, or it doesn't matter, either way? So the thing is that
relay, for example.
if you have a memoryless channel, then delayed information is kind of useless, right, in kind of a classical setting. So where delay comes in is if you have feedback or if you don't have a memoryless channel. And how to, I mean, we've done some work on studying delay, but I think that in my view, the place where it's interesting to look at delay is in feedback. Because in the circuitry, the delays are small, right? I mean, we're transmitting at such high data rates, and the circuits are processing the information so quickly that I don't think there's a lot of interesting problems to look at in terms of the delay in the processing. But as soon as you go to feedback systems, then delay becomes a huge issue, especially if the channel's time varying, because things might change by the time you get back. All the work that we're doing on delayed CSI and noisy CSI. So I think that's where the interesting problems associated with delay are, is when you have a feedback channel. In terms of processing delay, at least in my experience, it's small enough that it doesn't really come in to be a fundamental limit in receiver design.
Okay, thank you.